guys, today we're going to be learning two topics. The first one is called the Intermediate Value Theorem, and the second one is Boundedness. Intermediate Value Theorem is commonly abbreviated IVT. IVT says that if a function defines a polynomial with only real coefficients, and if for these real values, a and b, the values of f of a and f of b are opposite signs, then there exists at least one real zero between a and b. So what this means is that if I have two values and the y value for one x is positive and the y value for the other x is negative, then that means that there has to have been at least one point where the function crossed the x-axis in between those two values. Take, for example, this graph that we have here. We'll see the equation is given to the left, and the question asks if there is a zero on the interval of 3, 4. So if we look at the x values of 3 and 4, we have the x value of 3 is negative, the x value of 4 is positive. Therefore, yes, there does exist a zero on the interval of 3, 4. The way that we would prove this algebraically is we would find f of 3 and f of 4. Now, we learned in last chapter that if we wanted to find in a y value, we could use synthetic division and plug in the given x values. So first we're going to plug in the x value of 3. And we find that this value is equal to This tells me that f of 3 is equal to negative 30. By similar work, I can find the value of f of 4. And here we determined that f of 4 is equal to 72. Now, if I'm asked to determine if there is a zero on the interval of 3, 4, what we see here is the work that I would use. An explanation that I would give would be something such as, yes, there is a zero on 3, 4 because f of 3 and f of 4 have opposite signs. And that would look like this. Yes, there is a zero on the interval of 3, 4 because f of 3 and f of 4 have opposite signs. And that is it. The part in red is my algebraic proof. The part in blue is my summary statement. For the next two examples, go ahead and prove algebraically and make a summary statement to determine whether there is or is not a zero on the given interval. In the first example, we can determine f of 0 is going to equal 2 simply by knowing that if I plugged in 0, all of the x terms would disappear and 2 would be what I would be left with. To find f of 1, we do synthetic division and find that f of 1 equals negative 12. Therefore, I can determine there is a 0 because f of 0 and f of 1 have opposite signs. In our second example, we can also determine that yes, a 0 does exist on the interval of negative 1, 1. Now, an important thing that I would like to note is that if the opposite is true, it does not mean that a 0 does not exist. For example, if we see that two different x values would have both have the same sign, it doesn't mean that a 0 exists. It just means that there is not enough proof to determine that a 0 does not exist. We could have a scenario where maybe the x values, let's say the x values were 2 and 3, and let's say that the function looked like this. There are actually two zeros for this function that exist between 2 and 3. However, if I were to strictly find the function values of f of 2 and f of 3, they would both be negative. So I would not be able to determine that a zero exists with the IVT. So the IVT is not saying the only way a zero can exist is if the two different x values have opposite signs. It simply says that if they have opposite signs, then a zero for sure exists. The other statement that if the x values have the same sign, then a zero does not exist is false. Now we are trying to determine boundedness. We don't have a graph in front of us. This is a tip that we use to help us when we are doing synthetic division and we are trying to find if a value is too big and we should turn around, or too small and we should turn back the other way. The way that we can determine if a value is an upper bound is if all the signs in the bottom row of synthetic division are the same sign. Typically, they're going to be all positive. However, they could be all negative. The smallest integer that makes this true is called the least upper bound. Or lub. To find the lub, we are going to start at 1, then 2, then 3, and so on until we get all same signs. Notice that C must be an integer, okay? And that's why we start at 1, 2, and 3. Even if it's determined that there are no positive zeros, we still have to start at 1. And then 1 would be our least upper bound. When we are trying to find our lower bound is when all of the signs in the bottom row have alternating signs. And the largest C that makes this true is called the greatest lower bound, which we will abbreviate GLB, and some people will call the glub. To find our glub, we have to start at -1 and decrease the x values by 1 each time. Now, an important fact to note is that 0 is like a wild card. And what that means is that it can count for any sign that it needs to be, positive or negative, so that you can get the result that you want. So for example, if you are trying to prove that 3 is an upper bound, and you have the values of 5, 0, 6, and 8, then we can say that yes, this is an upper bound because all values are positive. If I were to have had the x value of -2, and I was trying to show that this was a lower bound, and let's say I had -2, 0, -6, 8, this could also work for me to say that -2 is a lower bound, because in this case I could let 0 equal a positive number. For our next example, consider this map of Fremd High School and its surrounding streets. If I were traveling in a car, and I were driving, and I was trying to find Fremd High School, in the direction that I'm going, it would be very useful if someone told me that once you get to Illinois, you've gone too far. If the same person had told me that once you get to Route 12, you have passed our school, that would not be very useful, because by the time I have gotten all the way up Rand Road, I have passed Fremd High School by several miles. The part that is the most useful is telling me the first street after I have passed Fremd High School. Similarly, if I were going the other direction, and I were driving this way, the street that would be the most useful landmark to me would be Euclid. Once I have gotten to Algonquin, I have already gone way too far, and Euclid would have been a much more useful reference that I had passed the high school. This is a concept that we are going to use as we talk about something called boundedness. In this first example, I'm being asked to prove that there is no real zero less than -3. Less than and a negative c-value means I'm looking for a lower bound. And when I'm looking for a lower bound, I want alternating signs. So what I'm going to do is do my synthetic division with -3 on the outside. And we get the following. At this point, I could draw the conclusion that yes, -3 is a lower bound because there are alternating signs in the bottom row. Now in the next problem, I'm being asked to determine if there is no real zero greater than 3. Because I'm dealing with a positive number and a greater than, I am now working with an upper bound, and when the upper bounds, I am looking for all same sign in my result row. I'm going to do similar work like I did in part A and do synthetic division. However, here I am now looking for all same sign. And I can see here that yes, this is an upper bound because the entire result row has all positive values. So I could say that 3 is an upper bound because there are all same sign in the bottom row. Now in this last example, I am being asked to find not only the greatest lower bound, but also the least upper bound. This is not something that we will ask you to do all the time, but when we do, you have to start at 1 and slowly increase your values until you find the first lower bound that works. To find our least upper bound, we start at -1 and slowly decrease our values until we find the first x value that works. You're basically trying to narrow the interval. So if you refer back to our example about Fremd, we are trying to find the first street on either side of the building to give somebody good landmarks as to when they have gone too far when they are searching for the building, or in this case, searching for zeros. So if I start with an x value of 1, I can work through my synthetic division. And we can see that in this case, I have all positive signs. Therefore, 1 is the first upper bound or the least upper bound. Now we want to go ahead and find our lower bound. So we start with -1 and go through the same process. Now right here, I can stop because I do not have alternating signs. Since I don't have alternating signs, that is enough right now for me to determine that this is not a lower bound. Now I'm going to go ahead and continue the process with -2. Again, I can see that this is not going to work and give me my lower bound. So I erase, and now I try -3. Alright, I'm off to a good start. I see alternating signs, so I continue. And as I complete the problem, I see that I now have my alternating signs. Therefore, -3 is my greatest lower bound. Now, a lot of times people wonder why this is useful. If you're doing synthetic division and you're trying to find zeros, a way that this is helpful is, let's say you try the value of -3, and -3 doesn't work. While it doesn't tell you an answer that works, it tells you that there is nothing smaller than -3. So this right here, when we see these alternating signs, it's kind of like a stop sign. It's saying stop, don't try numbers smaller than -3. And in this case, my all positive signs for 1 is very helpful. That's saying stop, don't try any x values that are greater than 1 because they won't work. 1 is an upper bound. And so this is very helpful because just by seeing this, I know that all of the real zeros for this function are going to occur between -3 and 1. And if I look at my possible rational zeros for this problem, since the coefficients have a 4 and a 5, I would have a lot of fractional possibilities here. And based on my greatest lower bound and least upper bound, that is telling me that several of these fractions between 0 and 1 or 0 and 2 are quite possibly the only rational zeros I have that will work. Alright, that's it for today. Good luck, guys. Consider this diagram that you see here. In this diagram, -2, -1, and 3 are all zeros. If I were to ask you what is the smallest zero, the smallest zero is -2. If we were to continue in the direction left of these zeros, then I could say that -3, -4, -5, all of those are zeros that are smaller than my smallest zero. If I were traveling in a car, I would say that all of those zeros are too far, that -2 was the last zero that worked. Okay? Now going in the other direction with my car, if I was trying to find the biggest zero that works for this function would be 3. Once I have passed 3, any other zero that I try after that is too big. 4, 5, 6, 20, all of those values are too big to be zeros for my function. So now if we consider the idea of every number greater than 3 is too big and every number less than -2 is too small, we can then think about what is called an upper bound and a lower bound. All of the values that are greater than 3 are considered upper bounds. All of the values less than -2 for this problem are considered lower bounds. They are considered that way because there are no zeros beyond the interval of -2, 3. All of the zeros for this function occur in between these x values. Okay? Now, if I was telling somebody the first number that was too big or the first number that was too small, this would be the first integer that is greater than the largest zero, or the first integer that is smaller than the smallest zero. And these are special because they basically tell me the first street after I have gone too far, or in this case, the first number that is too big to try for synthetic division. And we give these these x values special names. We call them the least upper bound, or lub for short, and the greatest lower bound, or glub for short. Please pause the video if the students need to continue sketching this diagram.